Hello, and welcome to yet another graduate video from Dr. Viv. We shall be exploring the concept of the moment of inertia tensor and evaluating it for a simple example, which is this metal plate that I've indicated here. We are to find the moment of inertia tensor for that plate as well as its principal axes. The most natural context in which to introduce the moment of inertia, there are two contexts you can do it. One is the idea of angular momentum, and the other is the idea of kinetic energy. I will take the energy approach, and in the process will be proving a theorem called Chasles' theorem. So our starting point is to draw a system of axes that are fixed. So this would be an inertial system, and I usually like to introduce the prime for the inertial system. So this is our system S prime. The origin is O prime, and from the inertial system, we refer to the actual body. So let the body's center of mass be at the point where the tip of this arrow ends. And now let's draw the rigid body. I'll define a rigid body later, but right now, let's just think of something that doesn't have any liquid in it, okay? So if you have this construction, you can keep track of any mass point within the rigid body by using a vector, which I'll call R alpha, where M alpha is the mass of the small mass point. Well, with respect to this origin, the location of that mass point is going to be given by this vector, which I'll call R alpha prime. The center of mass is located at a distance capital R. So these notations are consistent with the ones that I developed while talking about non-inertial frames in a couple of videos back. So that is my frame S. It's got the axes X, Y, and Z. And in general, the frame S could be rotating with respect to the frame S prime. So we already established in the video, I think it was video number 20, some things about the time derivative from this frame versus that frame. Right now, let's write down the obvious equation, R alpha prime equals R alpha plus capital R, which follows from simple vector addition. Okay, so the derivative, if I do the derivative operator, d by dt regarded from the frame S prime is d by dt regarded in the frame S plus omega cross. That's the operator definition of time derivative. Let's apply this operator to R alpha prime. So I'm going to get R prime alpha dot, I'm taking the derivative with respect to the S prime coordinates. Well, that's going to be this. So I get d by dt, just regular d by dt without any prime, plus omega cross applied to this vector, R alpha plus R. So I'm going to get a total of 3 terms. There is going to be no omega cross capital R. It only acts on this vector. So only a d by dt acts on capital R because capital R is not rotating itself. So I'm going to have R alpha dot plus R dot plus omega cross R alpha. Now we have to form the kinetic energy of the mass point and then sum it up over all the mass points to find the total kinetic energy of the object. So let's proceed to do that. The definition of kinetic energy, indicated by the symbol capital T, in the primed frame, it is 1/2 m alpha So the alpha particle will have that kinetic energy. Kinetic energy is squared. What does it mean to square a vector? It means to take the dot product with itself. So I have 1/2 m alpha r alpha, that's a prime dot, dotted with r alpha prime dot. Now, just to avoid writing r dot, let me use velocity. So I'm going to use the notation that this is equal to v alpha prime. Okay, so v alpha prime, and that will be equal to v alpha plus capital V plus omega cross r alpha. So I'm going to switch my notation from the dots because there are too many dots involved. So this is going to be 1/2 m alpha. Well, r alpha dot is this, so I'll write it down. So that's v alpha plus v plus omega cross r alpha dotted with itself. Now you just have to consolidate the terms. You're going to get 6 terms. So let's see what we get. The first will be 1/2 m alpha little v alpha dot little v alpha. Then you have 2 terms of the type v dot v alpha. It comes from v alpha dot v and then v dot v alpha. Well, v alpha dot v and v dot v alpha are the same thing because dot products commute. So I can consolidate them, those 2 terms, and write them as v alpha dot v. So that's 2 terms there. Well, the fourth term is going to be 1/2 m alpha v dot v, capital V dot capital V. And that's the 4, 5, 6 terms we need. Well, there'll be more than 6. There'll actually be 9 terms. So the 2 of those terms will consolidate based on the properties of dot product again. So I get omega cross r alpha dot v alpha. That's 2 terms there. And then you're going to get 2 terms that look like this, m alpha v dot omega cross r alpha. Wherever there's a dot product, you're always going to get 2 terms because dot products commute. And then you're going to get a unique term. So that's 1, 2, 3, 4, 5, 6, 7, 8, and 9. And there's 3 times 3, 9. So we're all set. I always like to count because that way you avoid mistakes. All right. Now what we're going to do is we're going to select the origin O as the center of mass. So if I do that, by the definition of center of mass, the definition of center of mass is R equals sigma m alpha r alpha divided by sigma m alpha. I have to emphasize here that the Einstein summation notation has been introduced, or rather used, because we are finding the kinetic energy of the entire body. So the summation over all the mass points alpha is assumed here. Repeated indices are always summed over. So this, in our in whatever happens above, is just written as m alpha r alpha over the total mass m. If r is taken to be the origin O, then this is 0, which means that wherever I see m alpha, r alpha, I can replace it by the 0 vector. If I differentiate this, I'm going to get m alpha v alpha is also 0. So I lose a lot of terms. I actually lose the second term and the fifth term. 1, 2, 3, 4, 5, the fifth term. Okay, because it's got a version of either m alpha v alpha or m alpha r alpha. So wherever I have m alpha r alpha, you get rid of that. Now we also have capital V alpha equal to 0. So that means there are no internal motions within the rigid body. So that'll get rid of these terms, these little V alpha terms, because there are no internal motions within the rigid body. That's what means to be a rigid body. So a lot of these terms simply disappear, and I'm left with just two terms, the two terms that survive all these things. So I write here the rigid body assumption. V alpha is 0, no internal motions. So the only terms remaining from this procedure is 1/2 the total mass. When I compute the total mass, it's going to be summed over all m for that one. So it's 1/2 capital M v squared, because v dot v is v squared. So this term disappears, this term disappears, this term disappears, this one is gone. So I just have this term and that term. 1/2 mv squared plus 1/2 m alpha omega cross r alpha dot omega cross r alpha. And that essentially proves Chasles' theorem, because this is equal to T space, the kinetic energy of the body regarded as a center of mass object simply moving in space. That's a translational kinetic energy. And then the rotational kinetic energy, which is T body. So this is also sometimes called T translational plus T rotational. So we have proved the thing that you probably knew in elementary mechanics in the most general setting. So that's the proof of the Chasles theorem. Now, to introduce a moment of inertia tensor, we're going to have to massage the rotational part a little bit. So let's focus on doing that next. T rotational is going to be 1/2 m alpha, and don't forget the Einstein summation is still in force over the index alpha. Now let's try to use this dot product. Let's try to use the Einstein summation convention. The dot product can be written in Einstein summation convention. When you have a dot a, you can write it as ak, where you sum over all the k's. So that's the Einstein summation notation. I'm going to use that here. So it's m alpha omega cross r alpha k omega cross r alpha k. So what I'll now do is expand the cross product itself. The cross product can be expanded using the epsilon tensor, because I'll recall to you what that is. If I have a cross b, the kth component of the cross product can be written as epsilon klm al bm. So I'm going to do things like that, except I'm going to use different indices. So that gives me 1/2 m alpha epsilon kij omega I r alpha j times epsilon klm omega L r alpha m. So you have to be careful to always use indices that are different in both these epsilons. There are plenty of alphabets, so it's no problem to do that. And please don't confuse this m with the mass. So now two epsilons, we can use the classic double epsilon identity now. So I'll move the two epsilons next to each other and use the double epsilon identity. It goes like this. If I have epsilon kij times epsilon klm, it's going to be delta il delta jm. So in other words, go directly first and then go crosswise. Delta im delta jl. So crosswise means im jl. Okay, then everything else you can just string it out. Omega I, omega L, R alpha J, R alpha M. Now we apply the delta operators. These Kronecker deltas are hungry and they have to be satisfied. Delta IL will attack omega I and make it omega L. Delta JM will attack R alpha J and make it R alpha M. So let's write that first. What will happen here? The IM will go and make this omega M, and the JL will go and make this omega J. I could make that L also, but I take the lowest hanging fruit, which is the first term that appears. So I have omega M, omega J, R alpha J, R alpha M. And now I'm going to write this first term in an interesting way. I'm going to write the first term as R alpha K. When you have repeated indices, you can choose any index you want. So I'll make the index M equal to K instead. So R alpha K. And then here, I'll write this as delta Lj omega L omega J. Now you'll see why I did that in a moment. And this one, I will do the following. I'll set M equals L, and that's about it, because here I have, no, I don't have M here, so I'm going to set M equals L, omega L, omega J, and J I'm going to leave alone. R alpha J, R alpha L, because I've put M equals L. So we're almost there. You observe that all this has been done, all these things. Here I could not have taken omega squared outside, because this is omega L, and that is omega M, omega J. So all this was done so that I could take out omega squared. In fact, I'm taking out omega L, omega J next. So 1/2 M alpha, omega L, omega J, times a bunch of stuff that will become our inertia tensor. So that's the thing we are after. R alpha K, delta Lj, minus R alpha J, R alpha L. This object that looks fairly scary is called the moment of inertia tensor. And it's written as capital I. So let's write it out. So this T rotational, T rot, is 1/2 capital I. The free indices here are L and J, omega L, omega J, where ILJ stands for M alpha times R alpha K, delta Lj minus R alpha j R alpha L, the moment of inertia tensor. Now, some books like to write this in a dyadic notation. So in the dyadic notation, you'll have this written like this. Dyads are precursors to the full tensor algebra. These days, we just stick with this. We don't worry about the dyadic notation. So that's the pre-dot and the post-dot and things like that. If you want to write it in terms of matrices, that is also a very popular way of writing it. This is omega transpose. I regard it as a matrix because a tensor of rank 2 is in fact a matrix. In this case, it's a 3x3 matrix because it's three-dimensional. So let's actually find out an expression in the XYZ coordinate system for the moment of inertia tensor. In the Cartesian system, what's it going to be? So if you look at this, when L is equal to J, those are the diagonal terms. So you're going to have things like, let's try to find what I11 is. It's going to be M alpha times 1 means x squared. So that's going to be x squared minus R alpha 1, R alpha 1. So that's basically x squared plus y squared plus z squared, because you're I'm sorry, that is this. X squared plus y squared plus z squared is R alpha k delta 1, 1. And this one, because this is not summed over, that's just going to be x squared. So this is just m alpha times y squared plus z squared. So the diagonal terms have the removal of the thing that the diagonal term refers to. So one refers to x, so you don't have x squared. Similarly, I22 will have m alpha times x squared plus z squared. Now, what about the terms that are off diagonal? And let me just write I33 also. It's m alpha times x squared plus y squared. If you have off diagonal terms like I12, then you're out of luck because this term delta 1, 2 is 0. So you're going to get m alpha times 0 minus, and this is still there. So this is going to be xy. So I12 is going to be negative m alpha xy. Similarly, I13 is going to be negative m alpha xz. And then I23 is going to be negative m alpha xy. Wait, 13 yz. So those are the components, and because of symmetry, these are equal to I21, that's going to be equal to I31, and that's going to be equal to I32. So we have all the components. Now, if the body is continuous, you don't want to be using these mass points. So the moment of inertia is integrated rather than summed over all the mass points. This summation is over all the alphas. So since alpha is not a repeated index, technically I have to put summation over all the alphas here. It's a little bit of a pain to do it. But most of the time, you don't have this discrete. In advanced physics, you never meet a bunch of point masses. So we have to integrate if you're given a density. So the most general expression, if you're given a density, is the integral over the volume. It's a triple integral. So I'll just draw 3 integral signs. The density function, which can be a function of r, so it can be a complicated density function. And then I'll string together all these terms I have here, y squared plus z squared, negative xy, negative xz, negative yx, x squared plus z squared, negative yz, negative zx, negative zy, x squared plus y squared, times the volume integral, so it's over dv, where v stands for volume. So in this manner, we have done the first two things. We have done the Chasles theorem, and we have introduced the moment of inertia tensor, and now we have to solve the concrete problem, which is to find the moment of inertia of that laminar plate. The one thing you'll realize is that the plate is two-dimensional, not three-dimensional. So what do I do with the density function if you have a three-dimensional density and not a two-dimensional density? Well, before we get into that plate, it might be a good idea for me to show how this formula is used in a concrete example. So let's try to find, even though it is not one of the things that I asked myself to do in the beginning of the video, let's try to use this formula to find the moment of inertia of something really simple. So we'll find the moment of inertia of a cube, because actually, believe it or not, the cube is easier than a square because it's three-dimensional. And then we'll move on to the square. So here's the cube. Draw it. You don't have to do the cube first before doing the square. I just thought, since these videos are educational in nature, it doesn't hurt to show a three-dimensional example first and then a two-dimensional example. So we have our cube. That's the origin. And we wish to find the moment of inertia tensor for this. That is the moment of inertia tensor. First of all, the cube is uniform density. And if nobody has stated it, I will state it now. Because it has uniform density, the function that we're going to use is going to be constant density rho naught. The volume element in Cartesian coordinates is just dx dy dz. And by the symmetry of the situation, it's pretty obvious that the principal moments I11 will be equal to I22 will be equal to I33, because the only thing that changes is the name of the coordinates. So it's going to be the integral from 0 to a. So I'll write a big 0 and big A, because it's 0 to a in all three coordinates, of rho naught times, let's just pick one. I'll pick y squared plus z squared, which is basically I11, times dx dy dz. Well, that's easy to integrate. The integral of y squared dy is just y cubed over 3. The integral of z squared dz is z cubed over 3. And the integral of dx is just x. So I'm going to get rho naught, because of the integral of dx, evaluated between the two limits, it's just a. And then for y squared, it's going to be a cubed over 3 plus this term, rho naught a times a cubed over 3. Same treatment for z squared. So we can write this as 2/3 rho naught a cubed times a squared. The reason I do that is because I realized that density times volume is precisely the total mass. It's always favorable to write things in terms of total mass, m, of the object. So I have the principal moment. Now what about the cross terms? By symmetry again, I21 will be equal to I31, will be equal to I32, and these are equal also to I12, I13, and I23. So there's only one calculation we need to do, and that's going to be negative because of the negative sign there. I'll just pick the xy term. Okay, so that's going to be another big 0 and another big A, rho naught xy dx dy dz. This time, x and y are independent in this cube. They're not independent. You have to make sure to split the range when you do multiple integrations. In this case, x and y are completely independent, so I can treat them as separate variables. And so I end up getting negative rho naught a squared over 2 when I integrate x, a squared over 2 when I integrate y, and a when I integrate z. And since I can pluck out rho naught a cubed and make it into mass, this gives me negative 1/4 ma squared. So that's it. We have found the moment of inertia tensor. Let me write it in the dyadic notation. I dyad is going to be 2/3 along the main diagonal and negative 1/4 everywhere else. Ma squared, and that's going to be ma squared over 12, 8 minus 3 minus 3, because 12 is a common denominator, minus 3, 8 minus 3 minus 3 minus 3, 8. So in this manner, we have found the moment of inertia of a cube. These moment of inertia computations are not that complicated. They just have to be done and done very carefully. That's all. So now we come to our main ambition, and that is to find the moment of inertia of the square plate. So this is what we are after. Not just that, we have to find the moment of inertia tensor as well as its principal axes. So what does it mean to find the principal axes? If you look at this moment of inertia that I found for this cube, it's got a bunch of negative terms. Now that you may wonder, what's the meaning of even having a negative moment of inertia? What does it mean to have negative effort to rotate? It's because there are three axes about which the effort is always going to be positive. That is called, those are called the principal axes. And that's why we need to find the principal axes in examples. Let's now work on this. The moment of inertia tensor, which I'll repeat over here, is going to be the integral over the volume rho of r times y squared plus z squared negative xy negative xz negative xy x squared plus z squared negative yz negative xz negative yz x squared plus y squared. I'm just copying what I have here times dv. All right, how to deal with a square plate? The square plate has got no rho. The proper density to use is sigma. So what we're going to do is we're going to introduce the so-called delta function. So it's sigma naught times delta z minus 0. The delta function tells you that this quantity is zero except when z equal to 0. And z equal to 0 means being on the xy plane. So the delta function can be thought of as an enforcer for the density to go from 3 dimensions to 2 dimensions. This is called the surface density. And the surface density is measured in units of kg per square meter, whereas this is measured in kg per cubic meter. All right. So if you wish, the delta function does have units, in this case, units of meters. Now we want to find the moment of inertia. It's very clear just by looking at it that two of the moments of inertia are going to be the same. Ix and Iy are going to be the same, because if you go here versus going here, you'll have the same effort to rotate this. So I'll do those computations together. I11 is the same as I22, and that's going to be the integral from 0 to a, the integral from 0 to a, sigma naught dx dy, because the dz part is gone thanks to the delta function. And I'll just pick the first one, y squared plus z squared, and the delta function enforces z equal to 0. Okay, that's the job of the delta function. Now, this can be easily integrated. That's sigma naught. That's y cubed over 0 to a for dx. Because z is 0, I just have y cubed over 3 there. So dx will give me a, and this will give me a cubed over 3. So the total result is sigma naught a to the 4 over 3. Now also, from the symmetry of the problem, it's clear that I12, which is same as I21, will be 0 to a, 0 to a, sigma naught dx dy times that element, negative xy, with the enforcement that z is 0. Well, x and y are independent, so that's going to be negative sigma naught integral x dx, which is x squared over 2. So that gives me a squared over 2. Same for y. So that's my second. Similarly, I13 will be the same as I31. So that's going to be the integral from 0 to a, sigma naught dx dy. All the integrations are going to be dx dy because dz is not there. Of the 1,3 element is xz with a negative sign. Well, if z is equal to 0, this must be identically 0. So anything with z vanishes. In the same manner, yz term will also vanish. So I won't write that. So likewise, I23, which is the same as I32, will also be identically 0. So the delta function takes care of a lot of things. Now the one term that's missing is I33. So let's figure out what that is. It'll be different because I33 represents the effort to rotate it about this axis. You can immediately see that the effort to rotate it about this axis is one thing. It's the same thing. But this is totally different because the plate moves like that. So I33 is going to be different. But we'll discover a beautiful relationship between I11, I22, and I33 in the process. So let's do that computation next. I33. So that's the integral from 0 to a, sigma naught dx dy, x squared plus y squared, with the enforcement that z equal to 0. Well, z equal to 0 enforcement is not even necessary because it is xy, pure xy plane moment of inertia. So this one is going to be a sum of two integrals. So it's going to be, I'll go back to my big 0 and big A notation. Sigma naught dx dy x squared plus big 0 to big A, sigma naught dx dy y squared. Well, that's interesting because you'll notice that I just did that computation here because this is when z equal to 0, you just have that, which is that. And when you have I22, it would be x squared plus z squared, which would be this. So this is the sum of those two terms. So it's sigma naught a to the 4 over 3 plus sigma naught a to the 4 over 3, which is 2 sigma naught a to the 4 over 3. So this is a very famous theorem called the perpendicular axis theorem, which I'll write here. So this, what we saw here is a specific instance of the perpendicular axis theorem, which says that I33 is always equal to I11 plus I22 for a laminar object. The proof of the perpendicular axis theorem is very trivial. It follows from the Pythagorean theorem. In fact, it's so trivial, I can give it to you in 2 minutes. If you have a laminar object and you have the z-axis, I've run out on that pen. The x-axis and the y-axis, and you have some mass point over here. Well, that mass point is going to be located at distance, which I'll call r alpha. The projection along the x-axis is going to be x alpha, and the projection along the y-axis is going to be y alpha. So the moment of inertia about the z-axis, which is I33, is going to be the sum of all m alpha r alpha squared. But by the Pythagorean theorem, r alpha squared is just x alpha squared plus y alpha squared. So that's going to be m alpha x alpha squared plus m alpha y alpha squared. But what is m alpha x alpha squared? It represents the effort of rotating it about the y-axis. So that's I22. And m alpha y alpha squared represents the effort of rotating it about the x-axis, because the relevant distance for rotating around the x-axis is actually y alpha. So that's I11. And that's a proof of the perpendicular axis theorem. It's always true for laminar objects. So now we have found all the elements. Let's gather them together and form our inertia tensor. First of all, the mass of this object is the mass density times the area of the square, which is a squared. So we can use that to write down the moment of inertia tensor. Can take out ma squared common. Now, when I take out sigma a squared, I'm left with a squared over 3. So because I've already taken a squared, m has already got an a squared, and there's an additional a squared that's taken out. So I just have to worry about the factors, numerical factors. So that's 1/3, that's -1/4, there's 0, -1/4, 1/3, 0, 0, 0, 2/3, thanks to the perpendicular axis theorem. Now I can take out 12 as a common factor, because 4 and 3 give you 12 as a common factor, ma squared over 12, and then I have 4, -3, 0, -3, 4, 0, 0, 0, 8. So we have succeeded in our ambition of finding the moment of inertia tensor for the laminar plate. Our next task is to find the principal axes, in which coordinate system you will lose all the negative numbers. Now, to cut down on my computations, I'm going to assume that ma squared over 12 is just equal to 1 unit. There's nothing wrong with this assumption. It just makes our life much easier, because we are interested in finding the principal axes. So the new inertia tensor, which I'll denote by I tilde, is going to be 4, -3, 0, -3, 4, 0, 0, 0, 8. And to diagonalize this, what we need is to solve the eigenvalue equation, IV equals lambda V. So this is a typical matrix eigenvalue equation, and this can be written as I minus lambda times the identity matrix in 3 dimensions, which I'll write as 1, 3 times V equal to the 0 vector. Now this has a unique solution by Cramer's rule if and only if the determinant of I tilde minus lambda times 1, 3 is equal to 0. So this is called the characteristic equation. So the eigenvalues are found, the eigenvalues are going to be lambda by solving the characteristic polynomial equation. So let's do that first. EV refers to eigenvalues. So I'm going to get, when I do, let me just write this out. I is 4, -3, 0, -3, 4, 0, 0, 0, 8, minus the 3 by 3 matrix multiplied by lambda looks like that, with a bunch of zeros everywhere else. That determinant must be equal to 0. So when you solve this, I get 4 minus lambda, -3, 0, -3, 4 minus lambda, 0, 0, 0, 8 minus lambda equal to 0. Well, it's easiest to use expansion along this column. So I'm going to do that. I'm going to expand along that column. So expanding this determinant in the third row, because of the convention that we have of this first row being, I should say, third column being plus, minus, and plus, although it scarcely matters since I'm setting everything to 0, I get 8 minus lambda times 4 minus lambda squared minus -3 squared, which is 9, equals 0. So now that's technically a cubic equation, although we don't have to be worried about solving a cubic because the solution just ions itself out. It's just a bunch of factors that are set equal to 0. So the first eigenvalue is 8. So I'll call that lambda 1. And then I have 4 minus lambda squared equals 9. So let's solve that. That's just a quadratic, which means that 4 minus lambda is either +3 or -3. If 4 minus lambda is +3, then lambda must be equal to 1. Let's call that lambda 2. If 4 minus lambda is -3, then lambda must be 7, because 4 minus 7 is -3. In this manner, we have found the entire spectrum of eigenvalues. The spectrum of the inertia tensor, I tilde, is going to be usually ordered from least to greatest, but since I've already called that lambda 1, I'll use that notation, 8, 1, and 7. Now, in a certain basis, the moment of inertia tensor will be completely diagonalized. Let's find out what basis will do that. That is the subject of finding the eigenvectors. So in that new coordinate system, the moment of inertia will be 8 along one axis, 1 along the other axis, and 7 along the third axis. And there'll be no negative things to worry about like these. So to find eigen vectors, which I indicate by EV with a vector sign on top of V, we have to solve the characteristic equation again, but with specific values of lambda. So what I have to do is 4 minus lambda 1. So I can write this like this. Okay, 4 minus lambda 1, -3, 0. So I'm just using this determinant, except writing it in a matrix form. Times the components of the vector, eigenvector v1. So I'm going to just call the components of the vector v equals v1, v2, and v3. So I have v1, v2, and v3 is equal to 0, which is 0, 0, 0, 0 vector. This has to be solved. Well, that's pretty easy to do. Let's write down what it is. Because lambda 1 is equal to 8, I'm going to get -4. All zeros, which makes sense because a two-dimensional plate will only have two-dimensional vector space. At least two of the vectors will be two-dimensional. you still need a third dimension sticking out of the page. So one of the eigenvectors will have a third component. So let's figure out which one this is. The first equation gives me negative 4v1, negative 3v2 equals 0. The second one gives me negative 3v1, negative 4v2 equal to 0. Well, it's pretty easy to convince yourself that this has, the only solution this has is 0 and 0. If you want to try this, you can put, the second equation tells me that v1 equals negative 4/3 v2. I can put this in the first equation, so that gives me negative 4 times negative 4/3 v2 minus 3v2 equal to 0, and that tells you that v2 must be 0. If v2 is 0, then v1 is also 0. So this eigenvector is going to look like this. Since v1 is 0 and v2 is 0 and v3 can be anything, you might as well take it to be 1. So this is the eigenvector with the most moment of inertia, because the moment of inertia associated to this is 8. Clearly, it's the correct eigenvector because this corresponds to having a rotation about the z-axis. The z-axis feels the maximum rotation effect of this plate, and so it makes sense that the highest moment of inertia is associated with the z-axis. So this is a fancy term for the z-axis. The other two values are going to be eigenvectors, rather, corresponding to the eigenvalues 1 and 7, are going to be in the xy plane. And you can already almost guess what they're going to be. Let's see if we can make an educated guess. 7 is pretty hard to rotate. So you might think of 7 as being associated to some line like this. So if I have a line like this is still pretty hard to rotate around that line. The easiest to rotate is going to be something like this, because all the mass points are really close to the axes. So just by looking, I can guess that this and this must be the two eigenvectors for the other two eigenvalues. Let's confirm our hunch. Okay, it's good to have these hunches. This is for lambda 1 equals 8. I've finished my lambda 1 equals 8 work. Now let's proceed to the other lambdas. Lambda 2 equals, let's try 1. All I have to do is put 1 there. So I'm just going to do it rather than write it out. It's 3, 0. And this eigenvector I'll call by the symbol u. Going to have u1, u2, and u3 as the components. And then I have 0, 0, 8 minus 1, which is 7. Let's see what happens to this system of equations. The first, I get 3u1 minus 3u2, and there's nothing there, equals 0. And then the second equation is negative 3u1 positive 3u2 equals 0. And the last equation tells me that 7u3 is 0. Well, the only way that can be satisfied is if u3 is 0. Now, how can we make these two satisfied? The first equation tells me that u1 must be equal to u2. The second equation also tells me the same thing. So that can be satisfied by making u1 and u2 the same. So I can take the vector u to be 1, 1, and 0. Now, normally it's considered polite to normalize it. So I'll normalize it by writing the length of the vector, which is the square root of 2, in the denominator. Last, and this satisfies our intuition, because the second, I'll indicate the principal axis here itself. The first principal axis is that's corresponding to, that's the eigenvalue v. The eigenvalue u is precisely this. These are all unit vectors, but I'm drawing them any which way I please because I've not been told how big A is. And the last unit vector is going to be this. In the xy plane, let's confirm it. Lambda 3 equals 7. So back to the drawing board, put lambda equals 7 over there, and I'm going to get 4 minus 7, which is negative 3. And then 8 minus 7, which is 1. And this eigenvector I'm going to call W with components W1, W2, and W3. So that times W1, W2, W3 must be equal to 0, 0, 0. Let's solve the system. That's what the first equation gives me. The second equation gives me identical equation. And the third equation gives me W3 equal to 0, which makes sense. These two equations imply that W1 must be equal to negative W2. Both of them give you the same answer. And so we have our W vector, which is 1 over root 2, 1 minus 1, 0. So this one, as predicted, looks like this. X component of 1, Y component of minus 1. So it would look like this. And the WW prime axis is the axis about which you rotate. The UU prime axis is that axis, and the VV prime axis. So these two axes, the W axis is associated with degree of difficulty 7, V axis degree of difficulty 8, and the U axis degree of difficulty 1 with the moment of inertias. So in that axis system, the moment of inertia tensor is completely diagonalized with the diagonal elements being 8, 1, and 7. So that completes all the parts of our problem.